Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss behavior of magnetic dipole in an external magnetic field, which is known as Larmor Friction. Precession means घूर्णन. Let's begin. Consider a nucleus of an atom. Here let the nucleus of an atom and electron is revolving around that of nucleus. Here is the electron moving around that of nucleus of an atom is nothing, that is equivalent to a magnetic dipole. Magnetic dipole. When the atom is kept in an external magnetic field, when that atom is placed in an external magnetic field, what happened? Then the electron orbit precesses. The electron orbit precesses about the field direction as the axis placed, as the magnetic field, that is the axis, and the precession of that of electron about that of axis. And this precession is called Larmor Friction, as far as the scientist Larmor introduced that phenomenon. According to his name, it was Larmor Friction, and the frequency of this precession is known as Larmor frequency. So the precession is known as Larmor Friction. Larmor Friction, and the frequency possessed by that of precession is known as Larmor frequency. Larmor frequency. When an atom is placed in an external magnetic field, a precession takes place in the orbit of that electron, and that precession is known as Larmor precession, and the frequency is known as Larmor frequency. Let us discuss it broadly. In an external magnetic field, let B, we prefer an external magnetic field. Let that one be the external magnetic field, B vector. This is the external magnetic field. In an external magnetic field, an electron is revolving. Let you take an atom here. Here be the nucleus, and the electron is revolving like this. The electron is revolving like this. Here we take the electron. This is O. Okay. The orbital angular momentum. Let the orbital angular momentum L. This is the orbital angular momentum. Of revolving electron the orbital angular momentum of that of revolving electron L is represented perpendicular to the plane of that orbit, and let the angle between L and B, let we prefer it as theta. Theta be the angle between L and B. The orbital magnetic dipole moment of that of electron, let we choose the orbital magnetic dipole moment, right here, orbital magnetic dipole moment that is mu L is equal to minus E by 2m L vector. When the magnetic dipole, that magnetic dipole is placed in an uniform magnetic field, see the external magnetic field means that is the uniform magnetic field that experience a torque, and that the torque is given by L vector, small l vector, that is the vector product of magnetic dipole moment and the magnetic flux density. So, the torque is given as, that is small l vector will be the vector product of the orbital magnetic dipole moment, that is the cross product of magnetic flux density, According to Newton's second law of rotational motion, torque is the ratio of change of angular momentum, means that torque further can be written like this. Again, L will be the rate of change of angular momentum, that is dl by dt, and the change of angular momentum takes place in the direction of that torque. So, in that of figure, let we show which one is mu and mu L, like this. We choose let we choose small portion here. is the point as C. This is the precession direction. Here is the torque, that is the torque, small l vector, that is mu l vector. Here is the mu l vector, electron. The point, let me prefer that point as P. Here that point P, let it be P dash. These are the terms like mu L, L, and how again L in terms of rate of change of angular momentum. So, OP is equal to L, OP is equal to L, and P dash is equal to dl, small length will be dl, that is dl. The change of angular momentum dl is perpendicular to that of L, and the torque L is perpendicular to that capital L, that is the angular momentum. So, angular momentum L remains constant in magnitude, but its direction changes as the goes on that of angular momentum L traces a cone around that external magnetic field B, so that the angle between L, that is the small l, and B external magnetic field will be theta, that is remains constant. Hence, the electron orbit around V, and it is the precession of that capital L. Okay. Let me introduce, if omega is the angular velocity of that of precession, omega be the angular velocity of precession, then capital L vector precesses through an angle d theta, that capital L precesses through an angle d theta. So, that small angle precession d theta will be omega into dt. Angular displacement is equal to angular velocity, that is the change in time. Angular velocity is equal to angular displacement divided by time. In that of time interval dt, it will be occurred. So, omega dt, therefore omega dt is equal to, that is dl divided by L sin theta, that is in case of a arc, if we consider a angle that is omega dt, that is the arc divided by radius. Here is the L, that one is the L sin theta. So, the angle will be arc divided by radius, that is the arc dl, and the radius will be L sin theta. Since it will be L, that will be theta, so that radius will be L sin theta. Putting here, or omega is equal to dl by dt into 1 by L sin theta. So, dl by dt is the L, or omega is equal to L divided by L sin theta is equal to L, that is the vector product of mu L and B. So the magnitude of mu L and B, so mu L cross B magnitude divided by L sin theta, that magnitude will be mu L B sin theta divided by L sin theta, sin theta cancel out. So we have omega is equal to mu L by L into B, mu L by L into B, that is E by 2m, E by 2m into B. Since mu L by L or omega is equal to, right here, E by 2m into B, that is the expression, omega equal to E by 2m into B, where E by 2m is equal to, that is mu L by L, mu L by L, which is known as the gyromagnetic ratio. This is the gyromagnetic ratio. That is the what? That is the gyromagnetic ratio, means it is called the angular velocity of Larmor precession, that is omega, angular velocity of Larmor precession, and which is equal to, the angular velocity of Larmor precession is equal to E by 2m, means that is the gyromagnetic ratio, means mu L by L, that is equal to the product of, we can say the product of magnitude of the magnetic field, magnitude of magnetic field, and the ratio of magnetic momentum. E by 2m means the ratio of magnetic momentum mu L to that of angular momentum L, and it is called the product of gyromagnetic ratio. That term will be the gyromagnetic ratio, and further we can say that the product of gyromagnetic ratio and that is the magnitude of magnetic flux. B is the magnitude of that of magnetic flux. This is the velocity of that of precession. Then the frequency of that of precession. So the frequency of that of a precession, Larmor frequency, Larmor frequency, Larmor frequency is equal to F, that is omega by 2 pi, that is omega by 2 pi, that is E by 4 pi m into B, that is the frequency, Larmor frequency. Omega, the value of omega, E by 2m, so the frequency, Larmor frequency, E by 4 pi m into B. The Larmor frequency is the independent of angle, there will be no angle term, independent of that of angle between L and B. L and B angle will be theta, but it is independent of that of angle. Notice that, note the theorem is very much useful for calculation of energy levels in presence of external magnetic field in atomic physics. So that theorem is a wide range of application in atomic physics. So with the help of this video lecture, you understand what is Larmor precession or the behavior of magnetic dipole in an external magnetic field. That Larmor precession results the Larmor theorem, Larmor theorem. How a atom behaves like a magnetic dipole, and when a magnetic dipole introduced in an external magnetic field, what happened? A precession takes place, and that precession is known as Larmor precession. We derive the value of Larmor precession velocity and the frequency which is known as Larmor frequency. So, with this useful and informative notes, let me wind up this session. Thank you.